Okay. Finally, it works again. So hello, everyone. Nice to see you guys. Finally, my camera is working. Sorry about this issue. Don't know what happened. So how are you doing, guys? Everything is okay?
I've tried reading about the chapter 7, right, in the book, I think, about work and conservation of energy. And while I understood most of it, I couldn't really understand the part about what was it again? Think spring with the springs with variable force.
Okay. Okay. Good. We can discuss this today. Yeah, let maybe wait a minute so more people join to us, and we can discuss this question with the variable force, ways how you calculate mechanical work with that. By the way, I wanted to let you know that you can check this Askar's YouTube channel. There are new videos with solution, like demonstration for solutions of these main most interesting problems from the previous homework. So you can go there and check everything what you are interested in. So okay, I believe most of people are already back. Again, sorry for this technical issue. And let us go to the discussion with work done by force and consider the option of variable force, which is not constant. So let me change the camera. Okay, so let us consider first and introduce the concept itself. So we have some reference point. Imagine we have some body on the surface, and there is some force exerted on this body, force F. Here is some angle alpha between the horizon and the direction of the force vector. And under the influence of this force, this body is moving to a new location, and there is some displacement, delta R, which is also a vector. So mechanical work, which is denoted as W, is determined as a dot product of two vectors. Vector F, our force, and displacement vector. So we know from previous discussions when we already considered the dot and cross products of vectors that the magnitude of this dot product, which will be a scalar number. So we remember that dot product gives us of two vectors gives us scalar number, and work is a scalar quantity. It will be equal to the magnitude of F times magnitude of displacement times cosinus alpha. So this is how we define work in a general definition of work. Also, what is important, if displacement vector R and the force vector are pointed to the same direction, mechanical work will be positive, will be larger than 0. If here is our body and here is the force vector and displacement will be in opposite direction, means that this force something like slows down some motion, but it still moves to the left. However, force is applied to the right. The work done by such force will be negative. So these statements are valid for constant force, so this equation, and that's not always the case. Definitely, that could be that force is a function of x, for instance, of position. Let's say here is our axis x, and depends on position, on its coordinate along this axis, force may change. In that case, force will be a variable, and we need to deal with this somehow. Let us consider such plot. Will be x, and here will be our force as a function of x. So we will have some dependence of force on position. The easy way to deal with this situation is to divide some large interval between x1 and let's say x2 into small intervals, which will be x, and here will be x plus delta x. So if this delta x is small, then we can, with some level of some like approximation, assume that we have some constant force within this narrow interval. So in that case, we can write some small work done by force by moving the body from position x to position x plus delta x will be equal some constant force within this narrow interval times the width of this interval. So now if we are interested to know which work will be done by this variable force while moving the body from position x1 to position x2, obviously we need to divide all this large interval x2 minus x1 into many small intervals and find work done at each small interval and then sum it up. So technically we need to integrate this, find the area under this curve, and means the integrate function f as from x1 to x2. So total work from going from x1 to x2 will be equal to the integral from x1 to x2 of this function f as a function of x dx. So then this is the approach how we get the work done by the variable force. And keep in mind here that we so far deal only with the one-dimensional case. So we have only x axis. However, in general, we need to define this also for multi-dimensional case, in particular two-dimensional. So let us go to the next slide. And in general, we can write the following. So let us consider two-dimensional space. And in two-dimensional space, we can write that work done from moving our body from initial point to final point, let's call it like this, initial, final, with some points in space, will be integral of the dot product of two vectors, vector of our force and displacement vector. So now in two-dimensional space, we can represent these two vectors in the following way. So force vector will be Fx times I unit vector plus Fy. So here is y times j unit vector. The same we can write for this dr for the change of displacement vector. Dx times I unit vector plus dy times j unit vector. So now we can substitute these equations into this integral, and we will get the following. So it will be integral from initial point to final point, Fx times I unit vector times dx times I unit vector. So we have scalar product of two vectors which are aligned along the axis x, like two components of x components of force and displacement vector. Then we have additional component from initial to final point, which is along axis y. Fy times j unit vector times dy times j unit vector. So this is the way how you approach this variable force, work done by variable force in two-dimensional space. So you need to integrate these vector products for components of force and displacement vectors along each axis x and y. And now let us.
Can I ask a question about these?
Yeah, sure.
So I know this may be a silly question, but the formula for work is F force and distance. But again, when we write for integration, often we add like dx to the end, right? So in this case, the dz, which d is it? Is it part of the integral, or is it
you mean dz, like the third axis?
Yeah.
Okay, so that would be also sure, we should have it also if we have third dimension. So this example was for two-dimensional motion, and that's why we have x and y. If we would have three-dimensional, it's just a bit more to write. That's why conceptually it's the same, but in order to save time, we just show one-dimensional and two-dimensional cases. But three-dimensional, you would have here another component fz as a function of z times k unit vector. This is for force, and here displacement would also have dz times k unit vector. And then you would have another additional component of this integral, because you need also take into account dot product of components of force and displacement vectors along axis z.
Oh, okay.
But conceptually, it's the same as two-dimensional case. You just add another axis. The biggest difference when you come from one-dimensional to two-dimensional, because you go from scalar cases when you have only projection on a single axis to vector form when you have components of your vectors along different axes.
I think, but my question was about a different thing. My question was about
Okay.
when in calculus, when we write about integrals, like there is this sign of the integration sign. Obviously, there's a b points,
Okay.
and then at the end we put dx in most integrals I've solved.
Oh yeah, yeah.
So this dz is kind of confusing because that dx is not like, it's not, this time it's displacement, right?
Yes. So what is confusing that we have here like this unit vectors?
No, confusing is that whenever we write integrals in calculus, at the end of every integral, we put dx. For example, integral, say, root of x dx, like that. So
Okay.
here, so in that integral, d is not displacement, but here d is displacement.
Oh, dx is displacement. So in this particular, so it's differential. Dx or dy is differential, and from mathematical point of view, it is differential, whatever it is, whatever it could be. But here we put some physical meaning in this integral. It's not just integral, but it's description of work done by force, and work done by force is product of two vectors. We have force vector and displacement vector, and dx times unit vector, it is displacement. So it stands for displacement, and we integrate along this displacement. So we integrate along axis x from initial to final point, and that defines our displacement along axis x. Here is displacement along axis y.
Oh, so
Mathematically,
dx after so in mathematics, dx after calculus is just the x-axis, but here it's some sort of we integrate a value into it, right?
Sure. There is just some independent variable. Differential of some independent variable means very small change of this independent variable. But that is general mathematical approach. However, when we do some integration in physics, we put some meaning in this, and in this case, dx, in this specific example, it is displacement.
Okay, now I understand. Thank you.
You're welcome. Okay, so now let us go and check some example how we can apply this to calculate work done by variable force. So let us maybe go to another slide so we have more space. And consider such system. So we have a spring and a body attached to the spring. It stays in equilibrium condition initially, means here we have axis x and here is 0. So equilibrium condition, there are no forces, neither from outside nor from the side of the spring. Now imagine that we apply some external force F to this body, which is pointed towards left. So under this force, the spring will be compressed and the body will move to a new position, like again, equilibrium condition under this force, external force applied. Let's show it here. And this position will be some coordinate minus x. In this case, we will get some reaction like from this string, which will be string force. And this string force, let's call it Fs, will be equal to minus kx. So it's always opposite to the displacement vector. Now imagine that we release this body, take off applied force, external, and this body will experience only string force, which will push it back to equilibrium condition, like from left to the right. So now let us calculate the work done by this string force. And keep in mind that the string force, kx, that this string force is not constant. It changes while the body is moving along axis x. So that's what we need to take into account, and obviously we need to apply this integration approach. So now let us consider motion from minus x to 0. So minus x to 0, work done by the string force. It will be integral from minus x to 0, initial and final point, of minus kx dx. So this is our force, minus kx. This is displacement, dx. So now if we integrate it, it will be minus kx squared divided by 2 from minus x to 0. Now let's substitute these boundary conditions. We will get minus. Here we put first 0, so it will be 0. And then we have minus kx squared divided by 2. So here what we see, we have minus here and minus here. So they cancel each other, and we have some kx squared divided by 2, which is larger than 0. So we see that work is positive, and that is because the body is moving from the left to the right, and this spring force is also pointed from the left to the right. So they coincide in direction. That's why we get positive work after integration this, because our force is not constant and changes along the displacement. And we get some positive value. Now let us consider the development of this situation. So obviously we don't take into account any friction. So in this case, if we come back with the string and this body to initial position, it will continue moving further because it will already accumulate kinetic energy, which we can discuss a bit later, and will continue moving to the right side until some coordinate, some positive coordinate x. So let us show it here. So this, initially our string was compressed. Now our string is stretched. And this is a new position here, which is position x. In this case, from 0 to x, our object is moving from left to right. However, starting from position 0 and further to positive x, our string force will change the direction and will be pointed backwards. So these guys are in opposite directions. Let's see what we get when we calculate this work. So work done by the string force from moving the object from 0 to x will give us the following. Here will be also integral minus kx dx. And here we will have initial point 0 and final x. So this will be minus kx squared divided by 2 from 0 to x, and will be minus kx squared divided by 2 minus 0. So here we have eventually minus kx squared divided by 2, which is smaller than 0. So you see that when we have different orientation of displacement, like opposite orientation of displacement and force vectors, we get negative work done. Now, if we consider work done by moving the object from minus x to x, it could be represented as the sum of these two works which we calculated, moving from minus x to 0 plus work done moving from 0 to x. And eventually we will get 0, because here we have plus kx squared divided by 2, here is minus kx squared divided by 2. So total work is equal to 0. In general, if we want to write work done by string force from moving the object from any arbitrary initial point to any arbitrary final point, we can write integral from x1 to x2 minus kx dx. This will be equal to minus kx squared divided by 2 from x1 to x2. And finally, we will get this. It will be, so taking into account this minus, it will be kx1 squared divided by 2 minus kx 2 squared divided by 2. So this is general equation for the work done by string force, which is a function of position x. Okay, I think that now we should proceed further. We introduced already work, and we can now start with kinetic energy. So, as you may remember from our previous discussions, there was some kinetic equation derived, probably one of our first lectures, which relates the displacement with velocity, taking into account uniform acceleration. So if we consider, let's say, uniform acceleration, then we can, let's say we have some body, have some force which acts on this body. Obviously, it will move with some acceleration. This acceleration will be F divided by m, which is mass of the body. And taking into account this equation which I mentioned before, we can write that v, some velocity v squared is equal, which will this body gain will be v1 square. It is initial velocity. Let's call this v2. It will be final velocity. So v1 square plus 2a delta x. So we consider here some axis x. This body is moving with some initial velocity v1, then we apply force, and it moves to a new position along axis x, and this displacement is delta x. So now we can substitute instead of a this expression with force and mass. So it will be v2 square is equal to v1 square plus 2 times f divided by m times delta x. Now let us rearrange a bit this. Let's put this velocity vector, like this velocity square, to the left side, then multiply by mass and divide by 2. We will get mv square, v2 square divided by 2 minus m v1 square divided by 2. It is equal to f times delta x. So these guys, we can call them K2 and K1, means kinetic energy at final position, kinetic energy at the initial position. And what do we see from this equation? That change in the kinetic energy, delta K, which is K2 minus K1, is equal to F times delta X. And this is equal to the mechanical work done by this force F at the displacement delta X. So this simple equation gives us so-called work kinetic energy theorem, which states that if the only change of work done by a force on the body is change in its velocity, in that case, the mechanical work done by the force will be equal to the change of kinetic energy. And obviously, kinetic energy is not the only form of energy which could be considered. In order to see the full picture, we need to proceed further and consider other forms of energy accumulation or change. So let us consider potential energy. So for this purpose, such an example. Let's say we have y-axis, and here we have the ground level. Here is, let's say.
I wanted to ask a question on the previous slide.
Yes, sure.
Thank you. Why did we write v2 square is equal to v1 square plus 2a? What does it mean, like plus 2a?
Yeah, so you remember
Oh, no, I understand now. Delta x is like the distance, so it becomes like speed, like
Exactly.
velocity.
So
Yeah, okay.
it's kinetic equation which relates velocity and distance without including time.
Yes. Okay. Sorry.
Okay, no problems. Okay, so let's consider such example. We have some object with weight m times g. So velocity v initial, let's call it, is equal to 0. So it just stays on the ground level. Then we apply some force and move this body to a new position, which is defined by coordinate x equal to h. So it goes from 0 to h. And then we keep this body in this at this height. So v final is equal also to 0. So some force external did work against the gravity, or we can call it in a different way, that gravity did some negative work because displacement was in opposite direction than the weight vector. And as a result, velocity didn't change because we have 0 initial velocity and 0 final velocity. So, however, definitely the conditions have changed. So obviously there should be some other form of energy, which is not kinetic energy. So let us determine work done by gravity force. So in this case, we go from 0 to h, and here will be minus mg dx. Minus because we have mg is going downwards and our axis is going upwards. Sorry, here it will be dy because we have axis y, and displacement is along axis y. So in this case, we will get, these are two constants, so we will get just m minus mg y, and y is changing from 0 to h. So it will be minus mgh minus 0. And eventually we will get some minus mgh. So work done by gravity force when we increase the height of the body without change of velocity in between initial and final condition will be minus mgh, and this is potential, can be defined as potential energy as a function of y coordinates. So potential energy is depends on the position along axis y, and this position is defined by this h, the height where we put it. So in this case, we can write that external work, so this is work done by gravity, let's say external work by this force F is equal to change in potential energy. Since potential energy at 0 is equal to 0, we can arbitrarily choose any 0 level of potential energy then this change, this work is actually resulted in the potential energy of the system. Now we continue this consideration of this case, and then we have this body already here at the height h, and let it fall down. So if we let it fall down, we had, now it will be different. We have initial velocity here is equal to 0, and final velocity is not kinetic energy. And this will, okay, do you hear me, guys? There's some issues with internet.
Yes, now we can hear
Yes,
you.
we can hear
Oh,
you.
okay. So now we can convert potential energy into kinetic. So we can write that delta U is equal to delta K. And we know that potential energy will be, yeah, so here should be minus. Potential energy will be mgh, and kinetic energy we know from previous slides, mv squared divided by 2. So we can put here final. So from here we cancel out mass and easily determine our final velocity, which will be like speed, will be equal to square root 2 times gh. So here we see that there is a conversion between, first we do some work and we this work is turned into potential energy, then we can convert it from potential energy back to kinetic energy. And we can write that kinetic energy plus potential energy is constant. So there is definitely a relationship. However, obviously, there is one more energy which should be considered in order to have the full picture of energy conservation. Means we need to discuss the internal energy, because there are some dissipating energy of the system because of, for instance, friction. And that is turning into heat. So this should be taken into account in order to have the complete energy conservation equation. That we will consider already on our next meeting on Friday. And probably we'll have some time for considering some examples how this conservation of energy will be applied for different situations.
Can I ask a question?
Yes, sure.
About the midterm exam.
Yeah.
What platform is it going to be on?
That will be long kappa, the same as you do the homework.
So will it be like, are we supposed to enter Zoom, or will it just be like a time limited long kappa?
No, it will be some time interval assigned for this midterm. You don't need to enter to Zoom or any other platform. You just go to long kappa in this dedicated time. Try to log in into long kappa a bit earlier, like maybe 20 minutes before the exam starts, just to be sure that not everyone is logging in the same time. There could be some issues. And then you just, you will see the problems, and we'll have some time to solve them. After the end of this time window, it will be submitted to for evaluation.
All right, thank you.
I will definitely soon, maybe today, tomorrow, I will send an email with some additional information to everyone, like as a reminder of upcoming midterm.
Thank you.
Excuse me, can I also like ask real quick about this week problem? I think that there is an issue with it, and I would like to address the question to you.
Okay, so I think that how it works we discussed with, if you believe that there is some issue with any problem, you make a print screen of the problem. You send also step-by-step solution, which you propose with your answer and answer from long couple. And then if indeed there is an issue with the problem, we will take this into account.
So we cannot discuss it now because I send it.
No. It's this homework. So we will discuss it only after this procedure when you submit the answer. We will discuss it with other instructors later and figure out if it was indeed some problem with long kappa or not.
All right, thanks.
Okay, thank you for attention. Have a good day and take care.
Thank you. Goodbye.
Thank you. Goodbye.
Bye.
Goodbye. Goodbye.
Bye.